I've already kind of mentioned earlier, I'm not a big fan of the electrophilic addition reactions because trying to find the pattern and way to group and categorize these as opposed to just looking at them as one-off reactions becomes a bit more challenging. But that's where we're at. So electrophilic addition, we're for electrophile addition because what we're doing is adding an electrophile to a nonpolar pi bond. These are primarily chapter 12 and 24. So like I said, again, I'm not a big fan of this particular section, but what I'm trying to do is come up with some way to look at patterns so that we can predict what's going on with these. Sorry, I had some technological issues. So when I went through and looked for patterns, the first thing I tried to do was address what's happening in the overall reaction. And the overall reaction is we're starting with a non-polar pi bond. So we're looking at carbon-carbon alkenes or alkynes, and we are reacting it with some kind of positively charged species. In this case, I'm referencing it as a Lewis acid. That Lewis acid could be a Bronsted acid, but that would fit in our chapter 11 section of looking at acid reactions. In all cases that I can think of off the top of my head, that Lewis acid isn't particularly stable, and so it's connected to some kind of leaving group. Okay? So after that, it's now, well, where do we see parallels and differences? And so this is where I saw these kind of sections, and I divided them into two different categories. We get a good, stable leaving group, and at the same time that we have a good, stable leaving group, the Lewis acid also has lone pair electrons, okay? So that those lone pair electrons can simultaneously donate back to our individual structure. And so if we think back to, say, our acid additions, and we looked at the acid additions, we have that Lewis acid of H+, and then connected to, say, a leaving group bromine, so a strong acid. Our electrons would come out, react with the hydrogen. We have that good leaving group, but we don't encounter the dynamics that I'm addressing here. We're not getting a three-membered transition state because the Lewis acid, that hydrogen, doesn't have an extra pair of electrons. Okay, that pair of electrons isn't there, which means we don't get the simultaneous reformation or pairing up with the forming carbocation. And so that's how the acid additions kind of take a step away from this kind of overall reaction. So if we look through kind of the patterns again, and what does this mean? If we look at this generically, the Lewis acid accepts electrons from our alkene. So if we look at this kind of pseudo-mechanistic, or not pseudo-mechanistically, if there's our mechanism written out, if we looked at this kind of stepwise, we're saying that first that's happening. The electrons from our alkene immediately go out to share with the Lewis acid, which causes a simultaneous, so we'll call it, let's see, how can I number this so we can recognize kind of the sequencing? Okay, we've got a 1, 1, step 1 of our, or part 1 of our first step, which forces a step 1, because it's still the same mechanistic step, but it forces a kind of a simultaneous leaving of our leaving group, and we get a simultaneous step 3 Lewis acid coming back to stabilize the forming carbocation. Why is the carbocation forming? Well, we just took those pi electrons and we moved them out. Okay, so as those electrons cycle out, in this case we're saying they're kind of cycling more upwards, that bottom carbon would have a carbocation form, so our forming carbocation. That carbocation, or where the exact placement of these, doesn't really matter because it's all happening simultaneously. And we know it's happening simultaneously because we only see one step, one reaction arrow, which is a bit kind of obnoxious to go through and do because we're now saying, oh, we know it happened simultaneously because we drew it that way. we know it happens simultaneously, mostly simultaneously, based off of experimental evidence, and that experimental evidence tells us to draw it this way. You as an organic student, unfortunately, don't get to do all of those experiments to equally prove it to yourself. You kind of have to take our word for it. Why? Well, this was chemistry discovered in 100 years. You don't have 100 years to learn all this, okay, or to verify this on your own, so you do have to trust us at some point. So some of the patterns that we can acknowledge is that by looking for these, we can see these same kind of intermediates and transitions show up. The result of this is that we do get this three-membered ring, okay? Which you might notice is particularly unstable because bond angles and all that fun stuff that we learned back in OChem 1, probably in Unit 1, regardless of where you took it, because of that, those carbons being sp3 hybridized and wanting to be 109.5. The bond angle in a three-membered ring is 60. So we're getting some massive kind of ring strain, I think is the name for it. You'll note that the next step here, I've got with a question mark associated with it. And we do have mechanistic arrows suggesting that that next step happens. But we do have to kind of evaluate our overall mechanism. And that's really going to key in on what is in that now red circle. If that is a positively charged atom, that is unstable. So we're now getting two contributing factors to this being like, break me apart. Right? We've got a positive Lewis acid connected to our structure and ring strain. Those two pieces together say this needs to continue on, and that's where a nucleophile, which could be the leaving group, can come in, do the ring opening, and we would get our final structure, okay, where we've added both the Lewis acid and the nucleophile across the pi bond. Why is it important to evaluate this mechanism? Well, if we understand that our reagent is fitting into this category, this becomes helpful because what we can now do is talk about how the mechanism produces things. And so that's what's being shown down at the bottom. So that when we go through and think about an individual reaction, we want to evaluate structure and the mechanism because those tell us stereochemistry and regiochemistry. The regiochemistry has to do with where our positions are located. Where do we have the Lewis acid relative to the nucleophile? Okay. Well, a lot of that comes from all of these individual processings all the way through. Okay. And ultimately, that first step is irrelevant. It's going to come in with this nucleophile. Right? Where is the nucleophile attacking? Is it attacking that carbon or that carbon? And in this particular case, it's identical, so we don't see a difference. Right? But as we go through and evaluate these things, that's what we need to be considering, where those pieces are going to go. Right? To help with that, that regiochemistry can really come into play by addressing the positive-negative characteristics of our starting materials. A Lewis acid is going to be positive. Our nucleophile or leaving group will be negative. We would expect the Lewis acid to pair up with the most negative and the nucleophile to pair up with the most positive. Okay? So if we can address those balances in charge, that's looking at our structure and where our electrons are located, so our electronegativity, that can help us predict the regiochemistry, where the Lewis acid and the nucleophile are relative to each other. The next part is the stereochemistry. Okay? In that stereochemistry, we've generated stereocenters at those two positions. So now what we're asking is, should this be wedged? Should it be wedged dashed? Should it be dashed? Should it be dashed wedged? So we've got all of those kind of possibilities sneaking up on us. That mechanism helps us to predict that stereochemistry. And if we go through and look at this particular mechanism, the nucleophile comes in as the Lewis acid bond breaks. Right? So that's the formation and breaking of a bond at the exact same instant. Okay? That sounds an awful lot like an SN2 reaction, because it is. And because it is an SN2, we're seeing a backside attack. So if we identified that our Lewis acid was wedged, the nucleophile would have to come in dashed. Right? Because we understand the mechanism overall, we know that that relationship is there. Okay? Are there other ways to go through and do this? Yes, abso-freaking-lutely. Memorization. Okay? So you either understand what's happening within this, or you just memorize the end results. You can absolutely get through organic chemistry memorizing. There's a lot to memorize. That's why trying to find these patterns to help kind of group things is a better option, I think, than rote memorization. Okay? So that's our first category for our electrophilic addition. We have a stable leaving group, and our Lewis acid kind of secondarily as a feature is also a nucleophile. Okay? If we move to the next category, the leaving group is unstable. Okay? Because the leaving group is unstable, it must be immediately stabilized. Okay? So how does that change our reaction? Right? Well, the alkene is still going to react as that nucleophile. It's still going to share electrons outwards. But as it shares the electrons outwards, we end up forming a very unstable leaving group. That unstable leaving group can't exist for a long period of time, so immediately stabilizes at the forming carbocation. Okay? How do we know where those pieces should go? Again, that's understanding our regiochemistry, and that's noting that we've got this negative positive dynamic in our starting materials. Whoops, of course I drew the charge there wrong. Negative positive. Okay? For those of you paying attention, you may have noted for the alkene, I drew the charges in a different location. This alkene is symmetric. It doesn't matter where we associate it, which means when we go through to look at our Lewis acid in our leaving group, okay, there is no regiochemistry that we need to be concerned about because of the symmetry of the result. Okay? So our regiochemistry we don't have to worry about. Well, what about the stereochemistry? Because this is happening simultaneously, there isn't enough time for any kind of bond rotations or manipulations, which means if the Lewis acid is attacked, okay, from above, the leaving group must also come in from above. Okay, so we don't get that kind of trans system that we saw in the previous case. Okay, so again, by categorizing these things, we can get some of those patterns down so that when we look at a reagent, we can think about these underlying patterns to be able to predict the chemistry, as opposed to memorizing the reagent to get to what the chemistry is. Okay? So there's a balance between those that we need to be considering when we evaluate these. Okay? If we're going to go through and kind of group these things, the top one is what's known as an anti-addition. Why anti? Because they're added on opposite sides. So it's very reflective to the Newman type terminology that we've seen in the past. In the bottom one, they're being added to the same side. So we could go through and call it a cis. This is adjective, adverb, English nonsense that you don't want to worry about. Not cis, but a syn addition. Okay? Just like with the first set, we do get the potential for a second reaction. That second reaction has a lot to do with what these pieces are, be it the Lewis acid or the Lewis acid in the leaving group in my labeling. Right? If those pieces are normal atoms, which we'll see here in a second, then we don't need to do a second step because they're normal. There's no extra chemistry we have to address. But if they're not normal, then we need a second step. Okay? And this, I would argue, is extra irritating with the electrophilic additions, is that secondary step typically aren't really responsible for the mechanism. You're responsible for knowing the end conclusion. This is where the memorization can come in, and you can help kind of supplement your understanding with some memorization on the bottom. Okay? So what we've got here is a big conglomeration of reagents that are associated with the electrophilic addition with electrophiles. So what you should be able to go through and do for each of these, given that starting butene, 2-butene, if we want to get specific, is decide what category we're going to fall in. Okay? Should this be a 3-membered transition? Should it be a 4 or more transition? By coming up with that categorization, we can help to guide ourselves to the end goal stereochemistry for each of these results. Okay? So I'm going to walk through 2 of them, and then I'll ask some questions about some of the others. You should ultimately go through and think about all of these, and I'll point out a cheat here that is kind of an artifact of how I've color-coded these. So let's start with the BR2. So again, if you haven't noticed already, a lot of this course is driven off of structure. So the first thing that we should go through and do would be to draw the structure. Now that we have that structure, we need to address our Lewis acid. So BR2 is a fun one because most people look at it and go, oh, there's too many electrons. It can't possibly be a Lewis acid. But since bromine is electronegative, it could withdraw those electrons, thereby making that first bromine our Lewis acid. So there it is, followed by our leaving group. So there's the pattern with it. Okay? So now what we've got to do is address, where does this structure fit? Do we have a stable leaving group? Well, Br- would be our leaving group. And since Br- is very large, it can stabilize that negative charge exceptionally well. So yes, we have a stable leaving group. This should already shuttle us into that 3-membered transition state, right? Or 3-membered transition possibility. But we should also verify that our Lewis acid is still a nucleophile. And if we go back, does the Lewis acid have a pair of electrons? Yes, it does. So Br2 fits our 3-membered transition. Okay, so I would identify that as a 3. This means when we look at the geometry of our final product, when we add those 2 bromines across the pi bond, we would expect them to be trans. Okay, we're getting an anti-addition. So by picking out some of those kind of nuances, we can predict where those things are going to go. Okay? And I just realized that all those other letters are confusing at the moment, so let's clean those up. So let's look at the next one underneath. We've got our H2 and platinum. Again, we should go through and draw out our structure. So there's H2. Well, we might be like, oh, it's got to be a 3-member transition state because it's matching the pattern of Br2. Don't match patterns to atoms, match patterns to categories. So in our category, we have to decide, is our leaving group stable? Well, in this case, our leaving group would be H-. Okay? There's our leaving group. There's our Lewis acid. Is H- a stable leaving group? Okay? Well, for the same reason that bromine was a stable leaving group, H- is not. H- is insanely small, which means this is a horrible leaving group. Right? Because it is a horrible leaving group, this reagent is going to fit under the 4+ transitions. Okay? We could take this a step further and look at the Lewis acid and decide, is it a nucleophile? Are there any electrons, lone pair electrons on the hydrogen? Nope. So all the more evidence to suggest that what we're looking at here is the 4-member transition, which means when I go through to draw in the product, those 2 hydrogens need to be added on the same side. Okay, so they should both be wedged. Okay, for those people being extra nitpicky, awesome, fantastic, I actually like that. Okay, you might also note that there's hydrogens here and that we wouldn't be able to tell the difference between all of those hydrogens. You're right. What we're trying to show here is that structure based off of the chemistry. We're assuming we can identify it because of what we can see. After we've drawn it, we could then evaluate and be like, yep, I can't tell a difference, so I'm not going to worry about it. Okay, separate system. Okay, so with that, what I would like you to go through and do is take a look at some of these other ones. You should go through and process them all, but I'm about to pop out some quiz questions about how you would categorize at least a couple of those. And now what I'm going to do is also throw in another system here. You might have also noticed if you're looking for patterns, which is good. I like that. Good on you. If we go through and look at these, if we're looking for deciding 3-membered versus 4-membered, 3-membered, we already have 2 atoms based off of the alkene. We're just looking at 1 extra atom. Nope, only 1 atom is highlighted. Note with the H2, the 2 was highlighted. Why? Because there's 2 atoms. So 2 plus 1 got us our 3. 2 plus 2 gets us the 4. HBX2, 2 atoms highlighted, 4. Mercury, 3. MCPBA is a bit of a cheat. I apologize on that. Again, you're responsible for structure. That's going to come in as a 3. We're really only adding 1 atom, the oxygen. O3, 4. OSO, 4. 4 plus is what I should be saying for those. The permanganate, 4 plus. Okay? And then the diazo compound at the end comes in as a 3. Okay? So what we're looking for is those patterns. I color-coded it to help kind of hint you out to that. Whether or not you decide to use that or think about it that way, that's up to you. Okay? So the next part here is now addressing some of the oxidation reactions that get tied to these. So a lot of these reactions will end, and we'll see why in quotes, with weird atoms connected. What are weird atoms? Well, if you go all the way back to OChem 1 from my class, we highlighted that we're looking at nitrogen, carbon, oxygen, halogens, and hydrogen. Okay, so it comes in about 10 elements. Boron is not one of those, neither is mercury, osmium, or manganese. Okay, so if we're seeing those weird atoms pop up, we need to somehow get rid of them from our overall structure. They're usually removed through some type of redox reaction. The mechanism you're not really responsible for. Okay? You are responsible for identifying oxidation versus reduction. The pro tip red box thing, that's kind of what that's addressing. Okay? So let's take a look at some examples. If I ran the borane reagent, okay, to get to this structure, what did I do? Well, I took, whoops, there's only 3 carbons. I took an alkene and I reacted that with BH3 and THF. When I went through and evaluated that, hopefully I would see that I don't have a good leaving group. This is a 4 plus reagent, which means the hydrogen and the boron are added to the same side. That becomes a bit tricky to deal with because the hydrogen becomes implied. Because there's already a hydrogen there, I don't have to specify the stereochemistry, and the boron goes at the other end, so I don't have to stress about stereochemistry at all with this. But I now have boron attached to the structure. I don't want boron connected to the structure. So what do? I have to follow this up with a step 2. That step 2 is peroxide and hydroxide. Okay? What that will go through and do is a rather interesting, fascinating mechanism that you're ultimately sort of not responsible for. And we cleave off the borane with hydroxide. Okay? So you're responsible for knowing that kind of extra piece. Okay? So if you wanted to kind of cheat, you could say the hydroxide is just replacing the borane. This one gets a bit misleading because we don't see any stereochemistry associated with this. That stereochemistry is largely centered on how that borane functions, and it's going to force that same kind of 4-membered thing. So if there was stereochemistry, we get retention, okay, which is an interesting one. We will see some reagents, particularly in this unit, to get us retention of stereochemistry. Borane tends to be one. Okay, so we're responsible for knowing that extra piece. Other ones, mercury. Okay, I don't want mercury connected, so I gotta get rid of it. Okay, the way to get rid of it is I add sodium borohydride. Okay, that borohydride, we're now not adding the borane. What we're adding is the hydride of that. How would we know? When we draw out our structure, again, structure becomes important. Yes, we'd see a negative boron, right? But boron doesn't want to be negative. And if we look at differences in electronegativity, hydrogen is actually more electronegative than the borane. So a hydrogen actually takes electrons with it and cleaves off the mercury. Okay, we do again get similar weird stuff going on with the borane. Stereochemistry, thankfully in this one, is rare to be addressed, but it can pop up every so often, so we won't stress about it. Okay? And what happens is we just reduce it. Okay? So these kind of secondary steps or reagents are things that you're required to know. Sometimes they're obvious, sometimes they're not. The osmium reagent, I'm particularly irritated at because you do need something to cleave that off. Sometimes it's shown, sometimes it's not. Very often it's not. It just says OSO4, and you're supposed to know that it's supposed to do all of its chemistry. Okay? Other reagents that sometimes show up instead of water, I think it is HSO3 minus or sodium thiosulfate or bisulfate, sulfite, sorry. What you're seeing there is ultimately some kind of secondary cleavage. That cleavage ends with the dialcohol. Okay, so you're responsible for knowing that extra piece, and that extra piece is important, but you're also responsible for knowing the mechanistic conclusions that come prior to this. Okay? And it's those prior to conclusions that are driving where the alignment is on everything within this. For instance, when we look at that particular structure, if we look at our intermediate, we have a 4+ membered ring, which means those oxygens are on the same side. Since we knew that based off of the reagents, when we get to our product, we would know they're on the same side. Okay? Again, not a stereocenter, so I don't have to stress about it. Okay? But it is something that you should be thinking about when you draw out these reagents. Sometimes those things pop up and you need to know it, sometimes they don't. So always draw it, and then you can always remove it if you don't need to stress about it. Okay? Permanganate, another one, follows the same pattern as the osmium tetroxide. The permanganate one can be a little bit different because we've got a bunch of different directions it can go. It can do oxidative cleavage, or it could just end at the diol. The secondary reagent isn't super clear within it. Ozone, extra freaking weird, does all sorts of goofy stuff, and to me, ozone is just a straight memorize, okay? Because there's just a lot going on with it. So what's happening here is we're again starting with that propene, and all we're doing is adding O3. This goes through, forms all sorts of weird stuff. This is technically our stable intermediate that then follows out, if you remember from our spider diagrams, either with just H2O or with DMS. What does that ultimately end up doing? Well, we're talking about cleaving, and it's a question of, do we cleave reductively and with the aldehyde, or do we totally cleaved? No, I did that right. The aldehyde and CO2, or do we cleave oxidatively and then with the carboxylic acid and CO2? Okay, where's the CO2? This is our CO2, 2 oxygens connected to it. All right, so it's all about how that thing kind of cleaves apart. That, again, because you get that differentiation being super oxidized versus less oxidized, ozone is a good one to just strictly memorize. Okay, so again, here we go. We want to identify these individual pieces. What I will go through and do is walk through you right now, identifying your nucleophile, where it is, and addressing, do we have to be concerned about regiochemistry? And then what I will ask you to go through and do is kind of solve out some of the other ones. And once you solve one through a little quiz question, we'll just pop up the rest of the answers. So, nucleophile present. Yes, there's a nucleophile present. That nucleophile is our nonpolar pi bond in all of these cases. Okay, so that ends up being our nucleophile. This can help. Note this one has 2 nukes. This can help us because that means the reagent we're reacting it with must be an electrophile. So by coming up with that categorization, it can help us work our way through. The next part is deciding, do we have any regiochemistry to concern about? So positive, negative, or negative, positive. In both cases, we're putting a positive charge or a negative charge on a secondary carbon. There is no way to differentiate that, so we don't have to stress about that one as far as regiochemistry goes. So regiochemistry is simple. We move to the next one, positive negative versus negative positive. Whoops, positive. Which one is the better system, green or red? Green is better because that's placing the carbocation on the tertiary position as opposed to the primary, and we now know where our individual pieces should be going. Whoops, come back here. Our oxygen needs to be going to the more substituted position. We would then follow that up with the hydrogen going in there in our second step. Okay? If we move to the next one, do we have a difference in regiochemistry, positive, negative, or negative, positive? Again, we do get that difference in regiochemistry, so we do need to be considering that when we move through this mechanism. I will say that this reagent is particularly interesting and messy, so I'll give you a bit of a hint on this process. We have identified our alkene as the nucleophile, which means we need to find an electrophile in here. Problem with that, hydroxide is a base or a nucleophile, okay? Which means the very first thing that needs to happen is with these reagents to make your electrophile. So consider that first before you start doing the electrophilic addition. Right? We move up to the top one with our concentrated permanganate. Concentrated permanganate and strong acid means oxidative cleavage. Right? We do have two potential nucleophiles, which means we need to be doing the cleavage at two positions. It's going to change the amount of products that come out of this. And we don't have to worry about regiochemistry here because we're doing cleavage. We're actually straight up cutting those apart. And that cleavage comes from, whoops, not from the H2SO4, comes from the hot, and it comes from the concentrated. Okay, both of those pieces tell us cleavage. And then our BH3 and THF, again, positive, negative, or negative, positive. Okay, we want the more stable carbocation, so tertiary, the black one was correct. Last one with the MCPBA, because I was mean and didn't give you the structure for the MCPBA in the past, let's go ahead and give it to you now. There's our MCPBA. Whoops. Now MCPBA. Okay, this is meta-chloro peroxy. Whoops, peroxy benzoic acid. A, B, P, C, M. Okay. So there are all those pieces. Spend some time to come up with at least a few answers on your own. We'll put a quiz question in here too. And now what we'll go through and do is just populate all the answers behind this. Okay. So in that first one, we've got the bromines adding to that. You may be like, but I didn't draw that. I drew that with stereochemistry where I showed wedged and dashed. Okay. Who's more correct, you or me? You are. Okay. That should be wedged and dashed because that's fitting our 3+ reagent. So we should be making sure to show that those are trans to each other. Okay. We do end up getting an enantiomer to this because the pi bond can attack both above and below. With the next one, we're going to get the OH and H added across the pi bond. We don't have a stereo center, so that's nice, but the regiochemistry becomes important. The next one, which was that tricky one, you're getting a 3-membered ring. So what happens with this one is that the reagents here turn this into the carbene, carbon, chlorine, chlorine, and an empty p orbital. Okay? Not a positive carbon, but an empty p orbital. That becomes important because the pi bond can donate the electrons in, and then since we don't have a good leaving group and we have that pair of electrons, we can share those electrons back, and we get our 3-membered ring that comes out of this. Because it's attacking on the top in this particular product, we also have to worry about the bottom. So we might go through and say plus enantiomer. And we would be wrong. The reason we would be wrong is that that carbon isn't changing its stereochemistry. It's not plus enantiomer, it's a diastereomer. Right? We can't just say plus diastereomer because there's a ton of possible diastereomers that could come out of this. We would actually have to show it, okay? Which is a bit frustrating, but we would technically have to show it. Okay. After that, we get our cleavage, our full cleavage, and note that we're getting, whoops, it's poorly done because this reagent does full oxidation, which I did not show. These need to be carboxylic acids because of that full oxidation. Permanganate is not a nice reagent, and we'll do full oxidation behind it. Okay. After that, we get our BH3. We'll again get an enantiomer here. Right? The thing that I would like to call out is note that we're getting a different result here, and it's not because the pi bond is located in a different location. Look where that OH is going. The OH in the BH3 is going to the least substituted position. The OH with the mercury reagent is going to the most substituted position. So those two reagents are very often in the same multiple choice set because they do the exact same chemistry. They add H and OH across a pi bond. But the stereochemistry of the H and the OH across that pi bond is very different. And that's why those will show up as the same or in the same multiple choice. So those are red flagged, in my opinion, for multiple choice questions. You should be aware of those differences. And then the MCPBA goes through and forms an epoxide. Those people being, but that's a three-membered ring. Remember, the three-membered ring I said opened when two cases were satisfied. Three-membered ring was one of them. The other one, good leaving group. Okay. We will look at epoxides later in this particular unit, just not in this video. Right. And with that, 40 minutes later, I think we're done. Let's check. Yep. Thanks for listening all the way through. It is very much appreciated. Let me know if you've got questions. Hopefully I can get my mouse to work. So long.